Hey everyone, welcome back. Today we are diving into episode 3 of our series on AI agent memory. If you caught episodes 1 and 2, you know we have been building up to this. Now we are getting into the real machinery. How does an AI agent actually store, organize, and retrieve memories? Let's break it down. Here is the uncomfortable truth about most AI today. Every time you start a new conversation, the AI has forgotten everything. It does not remember your name, your preferences, what you talked about last week. Nothing. It is stateless, like waking up with amnesia every single morning. That is the core problem that agent memory is trying to solve. To fix this, researchers at Princeton and Carnegie Mellon proposed a framework called CoALA, which stands for Cognitive Architectures for Language Agents. The big idea is that AI memory should work more like human memory, not one giant database, but 4 distinct types, each serving a different purpose. The first type is working memory. Think of it as the AI's active disk space. It is everything the agent is currently thinking about, your latest message, the last few turns of conversation, and the output of any tools it just used. Working memory is incredibly fast, essentially instant, but it has strict limits. The agent can only hold so many tokens at once, and when the session ends, it all disappears. This is your RAM equivalent. The second type is episodic memory. This is where the agent stores specific past events, time-stamped logs of what happened, when, and what the result was. It is like a personal diary. For example, the agent might remember that last Tuesday you were planning a trip to New York, and you mentioned that the Hall of Science was closed on Mondays. That specific memory is stored as an episode, and it can be pulled up later when you ask about similar trips. The third type is semantic memory. This is where raw experiences get refined into stable facts. If the episodic log says you complained about outdoor heat 3 times over the summer, the semantic layer extracts the pattern and stores a clean fact. This person prefers indoor, air-conditioned venues in hot weather. It strips away the specific events and keeps only the generalized knowledge. The fourth type is procedural memory. This one is about how to do things, not what to remember. It lives partly inside the model's weights, all the skills it learned during training, and partly in the system prompt and tool schemas that define how the agent should behave. In advanced systems, agents can actually update their own procedural memory by learning from past failures and writing better rules for themselves. Now, knowing what types of memory exist is one thing, but where do you actually store all of this data? This is where database architecture comes in. Modern agents use 3 main types of storage, and each one has a very different strength. Now, knowing what types of memory exist is one thing, but where do you actually store all of this data? This is where database architecture comes in. Modern agents use 3 main types of storage, and each one has a very different strength. The first is vector databases. These systems, like Pinecone or Milvus, convert text into high-dimensional numbers called embeddings. When you search, you are not looking for exact keywords. You are finding the closest meaning. So if you search for smartphone, it will also find phone and mobile device. The strength is fuzzy, semantic search. The weakness is that exact keyword lookups, like error codes or specific IDs, can actually get lost in the noise. The second is graph databases. Instead of storing blobs of text, graph databases store entities as nodes and the relationships between them as edges. For example, the New York Hall of Science is connected to the node for indoor venues, which connects to the node for the user's preferences. This lets the agent do multi-hop reasoning, connecting several facts in a logical chain, something vector search struggles with badly. The third is relational databases, also known as SQL. Good old-fashioned tables are making a comeback in agent memory. Why? Because they are efficient, auditable, and support exact keyword search through BM25 scoring. A vector entry might cost you 9 kilobytes. A SQL memory entry? About 2.8 kilobytes. That is a massive cost difference at scale. And unlike vectors, every row in a SQL table has a clear owner, a timestamp, and a traceable history. The smartest production systems do not pick just one. They combine all 3 in what is called a hybrid architecture. When you ask the agent a fuzzy question, the vector database finds the semantically related memories. BM25 narrows it down with keyword precision, and the graph database links the dots across entities and time. Together, they cover each other's blind spots. Let's talk about how memories actually move through the system over time. This is called the memory lifecycle, and it has 4 stages: extraction, consolidation, retrieval, and forgetting. Extraction is the first step. After each conversation, a background process, usually a small evaluator model, reads the raw dialogue and picks out what is worth remembering. Not every sentence gets saved. Only facts with lasting relevance. For example, If you say you are heading to Queen Zoo this Saturday and you hate waiting in lines, those two facts get flagged and extracted. Consolidation is the hardest step. This is where new memories get merged with what the agent already knows. If the agent already has a note that says you used to enjoy Queen Zoo, but now you just said you hate long lines there, the consolidation engine has to resolve that contradiction. It checks timestamps, weighs recency, and either updates the existing memory or records a version change. It is like editing a living document, not just appending to a log. Retrieval is when the agent actually uses its memory to answer you. When a new query comes in, the system scores all stored memories on 3 dimensions. How relevant is it to your question? How recent is the memory? And how often has this memory been used before? The top-scoring memories get loaded into the working context, and the agent answers based on them. Forgetting is the last stage, and it is just as important as the rest. If an agent never discards anything, its context gets polluted with outdated, irrelevant noise. Researchers call this context rot. The agent spends tokens on stale data, and its reasoning quality degrades. Intelligent forgetting is the immune system of a memory architecture. Now let's look at one of the most important engineering decisions in building a memory system. When do you update the database? There are 2 main strategies, and they make very different trade-offs. The first is hot path, also called synchronous updating. Every time a conversation turn happens, the memory extraction and database write occur right then and there, before the agent even generates its reply. The benefit is perfect consistency. What you just said is immediately remembered. The cost is brutal latency. Benchmarks show that full hot path memory updates can push response times to over 17 seconds. That is not a chat bot. That is a waiting room. The second strategy is background processing, sometimes called a sleep time agent. Here, the agent reads its existing memory instantly and answers you fast. Then, after the conversation is over, a background process wakes up and does the heavy lifting, extracting facts, resolving conflicts, updating the graph. The result? Response times drop from 17 seconds to under 2 seconds. Token costs drop by 90%. The trade-off is that there is a brief window where very fresh information has not yet been written to long-term storage. Engineers call this eventual consistency. Most production systems accept this trade-off. Finally, let's look at how intelligent forgetting actually works mathematically. Back in 1885, a psychologist named Hermann Ebbinghaus discovered that human memory decays exponentially over time. The longer since you last recalled something, the weaker the memory gets. Modern AI systems use this same model, but modern systems go further. They add 2 more dimensions to the score. First, recency. How many days have passed since this memory was formed or last recalled? Second, a recall boost. Every time the memory is retrieved and used successfully, its score gets bumped back up. So a memory that keeps proving useful becomes effectively permanent, while a one-time fact like it might rain on Thursday evaporates within days. Benchmarks show this approach reduces wasted tokens by 84% while doubling recall accuracy compared to systems that never forget. That's it for today. See you in the next one.